The title of my talk is Toward Automating Patient-Specific Modeling and Simulation in Biomechanics. So the patient-specific simulation pipeline starts with image acquisition in the form of MRI, CT, or ultrasound, followed by image processing and image segmentation, which involves essentially coloring every voxel in a scan, different material types. Producing a finite element ready volume mesh. If we're talking about nonlinear solid mechanics, we're mostly interested in finite element meshes. We need to apply boundary conditions and material models to perform analyses and ultimately make decisions. There's a wide topical breadth to this problem. We have image processing, computational geometry, finite element methods, and biomechanics, of course. There's been a lot of progress made over the last couple of years in speeding up this process. Still, there's much room for speed up in segmentation and mesh generation and in the analysis. And today I'll talk mostly about mesh generation and analysis. But I'll go through the whole process briefly. So medical imaging, just quickly, our imaging modality is MRI. MRI roughly measures weighted proton density of each point in a field. We stack two-dimensional slices together to represent three-dimensional data. The resolution of the images is on the order of millimeters. And ultimately, what's most relevant is it produces three-dimensional rectilinear grid of point intensity data that is fed into our image segmentation tools. So image segmentation, again, is the process of assigning a material type to every voxel in a scan. And unfortunately, it does require some degree of pre-processing of the image, usually in the form of smoothing filters, so that we can maximize the effectiveness of these segmentation techniques. There are many segmentation techniques out there: thresholding, region growing, level set methods. Neural networks have a promising future. Many others, but at least today, there's still a significant amount of manual fine-tuning that's required. And hopefully in coming years, somebody smarter than me can help further that along. But for now, let's say we have a segmented image through manual and automatic processes, and we want to produce a valid mesh. So there are really two main approaches we can take with this. Direct meshing, which involves we have a segmented image, which is essentially volume data. It makes sense to go directly to a volume mesh. The other approach would be to first generate a surface from the segmented image and then use a CAD-based volume meshing technique. We're actually going to opt for the second approach. Mesh design is less constrained in the sense that if we want to remesh to track certain solution features in time, or we want to do mesh refinement, it makes more sense to have a valid surface first. And we can do rigorous verification of that surface. And lastly, we have a surface to volume mesh tool that supports a high level of automation. So I'm going to sneak a surface generation sub-step in here, and essentially what we're looking for is starting with a segmented image to produce a valid watertight surface in the form of an STL or Stanford polygon or VTK file type, and to be fed into a volume meshing tool. So given a segmented image, we're looking here at a two-dimensional slice of a canine ventricles. We are going to loop through the image with pixelated windows and find regions where there are interfaces. So for each particular window, we approximate the interface by minimizing a relative error functional that compares geometric properties of the pixelated region to the approximated region. Once we've defined this parameterized curve, we put a point on that curve and an outward pointing normal, and we can generate an oriented point cloud. So in 3 dimensions, we have a segmented image. We loop through the image with these windows. We identify the locations of the interface, and we produce an oriented point cloud. This is the same oriented point cloud here from which we want to produce a surface. And this is a well-developed problem known as surface reconstruction. We have an oriented point cloud, and we want to determine, sometimes not oriented, but we have a point cloud and we want to produce a surface. So we use Poisson surface reconstruction to produce a smooth, valid, watertight boundary. Although it is too fine on the surface, it's on pixel resolution. And so we do an additional step known as decimation or surface coarsening using centroidal Voronoi diagrams. So at this point we have a surface mesh that can be used moving forward. So just quickly to summarize, this surface generation step is easily parallelizable. Each of these windows can be treated independently. We broke it into 2 steps. We first generated an oriented point cloud, followed by a surface reconstruction step. And these surfaces are closed, manifold, watertight surfaces. There are no hanging nodes or overlapping facets, non-manifold edges, things of that nature, and so we can feed that directly into volume meshing steps. So now we can finally move on to volume meshing. So just as a quick aside, for nonlinear solid mechanics, linear tetrahedra are generally not to be used. Not in tension, not in torsion, not in bending, not in contact. I'd be happy to share these or many other papers that describe and demonstrate why you should not be using linear tetrahedra. So in general, we want to use higher order tetrahedra or linear hexahedra in the context of conventional finite elements in nonlinear solid mechanics. The problem is that automatic hex meshing is still largely an open problem for general surfaces. And automatic tet meshers have their own issues with production of sliver elements or elements of poor quality. Not to mention quadratic tetrahedra can lead to more expensive computations. So we move towards generation of a hex-dominant polyhedral mesh, and then we will modify our finite element approach so that we can accommodate more general geometries, or more general elements, I should say. So we have a surface mesh. This was from one of the previous slides. We have a valid surface mesh, and now I'll walk you through that mesh procedure. So we create a bounding hex mesh. We sculpt that hex mesh with the surface using largely integer-based logic operations. And if we look at a particular slice in that, we end up with linear hexahedra on the interior, and we have arbitrary polyhedra near the surface. And as you can see, you can produce some pretty nasty shapes if you're thinking in terms of a conventional finite element approach. Before we get there, let me just compare this mesh to some meshes produced by some more other popular methods. So again, this is the mesh that we've produced. Linear hexes on the interior, and we have polyhedral elements near the surface. We end up with 240,000 degrees of freedom. Using simple wares plus FE grid, which has linear hexes on the interior and linear tets that are pixel resolution near the surface, we end up with 2.5 million degrees of freedom. Simple wares plus FE free uses the surface from the previous approach and does advancing front algorithm, and we're going to stick with quadratic tets, and it produces 427,000 degrees of freedom. TetGen is also a popular tetrahedral meshing algorithm. You can tell the quality of the tets are significantly worse compared to simpleware, although it does reduce the degrees of freedom somewhat. If you couldn't follow along with all of that, our polyhedral meshes produce a significant reduction in the size of our system. So not only do we guarantee a robust and fast meshing algorithm, but then now after the fact, once we actually want to solve these systems within our finite element scheme, we can run them faster because the size of our system is smaller. So now we need to talk about how we're going to handle these polyhedral elements, right? Because conventional finite elements can't require a mapping to a parent element space, and that's why we typically stick to linear and hexahedral elements, or tetrahedral and hexahedral elements, sorry. So I'll discuss briefly the partitioned element method, which is the polyhedral finite element method, for which shape functions are discontinuous piecewise linear functions over a physical element. And we enjoy finite element-like boundary condition enforcement and quadrature efficiency, like I said, without the topological restrictions on the element shape. And most importantly, it converges at the same rate as linear hexes. So that's as far as we've gotten so far with polyhedral elements. In our future work, we're going to demonstrate its viability in biomechanics. But just to close the loop, I'll show some results using conventional finite element approaches. With some of the work that we've done with Lawrence Livermore National Lab, they have some pretty powerful supercomputers that they want to use to perform an unprecedented exploration of mechanisms of cardiac arrest. So I won't repeat some of this just because from the previous presentation, it's very similar. We have conservation of linear momentum and compressibility, orthotropic, hyperelastic, passive portion of the material, as well as an active portion with an additive decomposition of that stress. Ultimately, we end up with a differential algebraic equation. After discretization and linearization, we apply a novel iterative solver to solve our system. I worked towards producing quadratic tetrahedra for this canine heart, ex vivo canine heart. So we started with raw data, we segmented the image, we produced valid quadratic tetrahedral mesh. We used the same Bayer paper for generating fiber orientations in the material model, applied boundary conditions, and ran some analysis, some pretty videos. The color scheme is plotting fiber stretch. And now we can start asking a whole slew of more interesting questions about possibly some of the things that were discussed in previous talks. So there's still some work to be done in terms of automating this process. Once we already have a lot of people doing some really interesting work in this field, but once we are able to really speed up this process and get it done in a much shorter period of time, we can answer a lot of interesting questions, and we can really start changing the industry. This is the picture from SimTK. This is really a state-of-the-art knee, and they're using hexahedral elements, and you can only imagine how much manual effort must have gone in to producing a mesh like this. We're not quite there where we could just automate that process, but once we get there, which is inevitable, I think we can do some really interesting things, such as quickly producing large data sets. And the dreamer in me thinks about, running clinical trials through simulation. There's a lot of things that need to be improved before that. We need better material property characterization. We need to automate a process for applying boundary conditions, certainly uncertainty quantification, verification, validation, and even high performance computing to speed up simulations, not just to run large problems, but to speed up smaller problems would be of use. I ultimately have an interest in knee orthopedic biomechanics, and if we make this a statistical problem, we can start providing statistical suggestions. And with that, I'd like to say thank you.